And then if you break down what total cost is obviously your fixed cost and your variable costs. So in the exam, you'll be given an example where you're told, a firm has X amount of total cost and variable cost of 2 Rand per unit. And you basically plug those variables into your total cost function, and you make your total cost equals total revenue. Is somebody trying to get in? I'm hearing something. Oh, somebody's just unplugging and replugging in their computer. And then we kind of did some examples with cubic functions, right? And we looked at the general form of a cubic function. You guys remember the only thing that really makes a cubic function any different from the stuff that we've dealt with before is that the cubic functions have an exponent, the highest exponent of 3. And because of this exponent of 3, their behavior is a bit more not random, but is a bit more unpredictable than your quadratic functions. So you can't just plug in use your negative b over 2a formula to find the minimum and maximum, or a turning point. Yeah, you have to kind of just plot the whole thing out and look where it crosses the y equals 0, right? Cool. So now let's talk about exponential and logarithmic functions. And this, for me, this was a really interesting section, because this is where we were introduced to what is called, Euler's equation, right? So let me open up the notebook, the study guide.
Sorry for that.
So if you would follow me, that's fine. This is not a lecture; it's just a study group. I'm not going to kick you out of my class or anything. So if you go to page 49, here we deal with exponential functions and logarithmic functions, right? And the most important thing to know about exponential functions is that they are functions that have the following form. So I'm going to start writing here. Exponential functions have the following form, right? You have exponential. You have this kind of fx or y equals a to the power of x. And there's something very interesting that happens when you. Sorry, just give me a second. So there's something that's very interesting that happens when you have x as the exponent, right? And I can only kind of really illustrate this by way of a graph. You have a graph like that, and you plot the values for y equals a to the power of x from -3 all the way to 3, right? So let's say we're not going to be covering negative y, but for our example, let's cover -3 all the way up to 3. Okay, I'm going to put this here like that. You kind of get this shape. And this point of intersection here, where this polynomial crosses x equals 0, is always at 1. Now, who can tell me why for any exponential graph, whether it's and I'm not going to go into the specifics of each graph.
I think anything to the power of 0 is 1.
Exactly. So all these exponential graphs will always cross over x equals 0 at 1, because anything to the power of 0 is 1. Just excuse my horrible graphing here. I'm getting used to using. I'm using a Wacom tablet pen that I got last week. So now let's go ahead and, just for example's sake, go ahead and plot some values, because there's a specific rule that you need to be aware of when you're dealing with exponential equations. So let's say we're plotting y equals y equals a, the function y equals a x. So if a is if a is 1, right? What is y? Can anyone tell me? If a is 1, then 1 is okay. So then x. I think there's an example. I think this is actually illustrated here. No, they don't have this example. There's there's a deeper explanation towards the back of the book here. Here we go. So here they have 4 as a, and what's happening is that at x equals 0, we get 1, right? And then for x equals minus 1, we get a quarter. And then for x equals minus 2, if base 4, we get an eighth, right? And then for x equals minus 3, we get a 16th. So what's actually happening is that we are dividing by the same sort of proportion, the positive proportion, right? So for here, for x equals 1, we get 4, and then we get 16, and then we get 64. So we're getting smaller by the same proportion, but we're never actually getting a negative number, like into the y equals 0 or y equals negative 1 territory. We're just tending closer and closer and closer to y equals 0. Now, that line that we sort of tend towards but we never reach, who can tell me what the name of that line is? In anybody at all want to take a guess what that line is called? It's called the asymptote, right? That line that we are tending towards but we never actually reach. So now, how do we determine how fast this line is increasing, or the slope of this line, right? That's determined by whatever a is, the base is. So obviously, if a is 2, then we might have this black line as is represented here. And then if a is 4, if this a, the base is 4, we will have a exponential equation that is increasing faster and faster. Then if a is 1, the exponential function is still going across 1, still intersecting x equals 0 at 1, but where the rate of increase of the specific graph is much slower. And then if you look at the examples that are given to us in the study guide here, all that they're saying is that if the base is minus, then we are dealing with a graph in the second and third quadrant, right? So if your base is minus, then if it's positive, we're dealing with a graph in the first and third quadrant. And then if your exponent is negative, then your graph is obviously decreasing, right? And the same goes for if your base is positive and your exponent is positive, then your graph is increasing. That's all that's being said here. The other two dropped out, so I don't know.
No, no, this is I'm listening. It's just that my mom is on the phone, so that's why I'm on mute. I don't want to disturb you. But yeah,
Okay.
I think we should continue. I don't know about you.
Yeah, no, I mean because I'm doing it for their benefit. I actually want to move over to the other content, but let's have a discussion around the stuff that I'm not super comfortable with, and maybe you can provide more clarity. But as I said to them, like I'm not gonna. This is not a lecture; it's a study
Yeah.
session.
So
And
like,
yeah,
okay.
okay, cool. So then let me continue. So now this graph of exponential, this exponential functions graph. Do you have I mean, what else can we say about it, right? So we know that if the exponent is negative, it's decreasing, so it has like this sloping down kind of shape.
Yeah.
But where might we find some real world examples where we might use this sort of exponential functions? Do you have any examples that you've come across in the textbook?
I don't think so. Not.
Well, so in terms of the rest of the section, they use they talk about limit unlimited growth, right, as an example of an exponential function. Unlimited growth,
Yeah,
and
I'm there.
cool. But before we go there, there's three rules that you have to remember, and these aren't actually listed here on the page as well. But these they give us some rules for dealing with working with exponentials. So let me find here working with exponent. There we go. Ah, here they are. So they say here if the exponents are different but the bases are the same, then when you are timesing the two terms, all you have to do is add the exponent. And they give an example here where 4 to the power of 3 times 4 to the power of 5, which obviously has the same base. If you're simplifying, you just say 4 to the power of 3 plus 5, which is obviously 4 to the power of 8. And then obviously the same would apply if you are minusing them, right? Sorry, if you're dividing, then you minus the exponents, right?
Yeah.
And then the last one that I think was is relevant to our discussion is this is how to treat the exponents when you are trying to find the exponents of a term that's in brackets, right? You just times them out. And it's very easy to kind of like get confused here and make a mistake of plussing the exponent where you should be timesing them. So just watch out because there were a lot of tricky questions in the practice papers where
Yeah.
we're dealing with this. Cool. So now let's talk about unlimited growth, which is obviously modeled based on the exponential function. So unlimited growth is modeled by the following function, right? You have if t. You, also, it seems like Nosi was disconnected somehow. Hi, Nosi. Welcome back. It looks like you got disconnected there for a moment, but we're just talking about unlimited growth. So the formula for unlimited growth is A times E. But now E is not a normal constant like we dealt with in the past year. E stands for Euler's number. Just remember that. So don't just substitute E in the exam with any number you come across. It's a specific number that's used quite commonly in maths. The number E, also known as Euler's number, it's a mathematical constant that's approximately this number and can be characterized in many ways. It's used in natural algorithm. Cool. So e to the power of r, which is another constant term, times t, which is the amount of time. So you would use this if you were maybe trying to plot trying to model the growth of a population, a specific population. Let's say a population of I don't know, birds on an island, right? An example that they give here is in 1980 on page. Oh, this is at the back, at the end of the textbook. So in the example that they give here, they say the following, right? In 1980, a specific village had a population of 753, and then now we have a point 753 over here. So at the beginning of time, or t equals 0, which is when we started tracking the population growth, we had a population of 753. And it is given that the population grows according to the following function, right? 753 times Euler's constant to the power of 0,03 times t, where t is an integer that represents a year. And what they're saying here that obviously you can substitute any number into t to get a specific year. So after 10 years, pop 10 equals 753, the base, times Euler's number to the power of 0,03 times 10. And if you know how to use a calculator, you can obviously times all of that out, and you'll get 1016. But now, what if we know, what if we have, or maybe a specific population count, and we want to figure out how long it'll take for the population to grow to the to that specific volume, or that specific number, like they've done here, where they have 3,500, and they want us to find t. This is where we would have to be very familiar with our logarithms, right? So here, what they've done is actually a mistake in the UNISA textbook. This should be 3,500 here, this value here. So we say we make 753 times Euler's number to the power of 0,03 times time. The subjects of our function equals 3,500. Obviously, if you divide both sides, you get this Euler's, right? And then we find the logarithm of both sides, right? So the logarithm of this 3,500 divided by 753, and the logarithm of Euler's number to the power of this specific variable gives us this line here. Now, a rule that I forgot but became very apparent to me when I was trying to figure out what is actually going on here is the fact that the logarithm of Euler's to any number equals that number. So if the exponents in this case, yeah, so Euler's x equals the log of Euler's number to the power of x always equals x, which is why it might be very useful to use the strategy when trying to find t in this case. So now we've taken out a variable from the function, and we only have t remaining, and all we have to do is obviously divide this 1.54 by 0.03 to find out how many years it will take to get to the population, a total population of 3,500. So, I mean, Samaguni, was that clear to you?
Very clear.
So now another rule that I didn't touch on earlier was that this property of exponential functions, which is that the function is continuous, it never ends, right? I did mention that the larger the base, the faster it continues, but in an exponential function you have this sort of unlimited growth. But what if you have some sort of carrying capacity? Let's say, like the Earth can only accommodate, hypothetically, let's say our Earth can only accommodate 70 billion people before we run out of resources and space to accommodate everyone, and out of money to accommodate everyone. So how do we then add a constant to our exponential function that signifies that there's a limit to how much growth we can have? And that's what's covered in the limited growth section, right? So we have the function for limited growth that's expressed by that's modeled by the following equation, right? Where we have the function of y equals a times 1 minus e Euler's number again to the power of minus by. And then they even say here that the examples of limited growth are, mechanical systems and electrical systems. And I mean, you can kind of imagine a mechanical system, right? Why it might behave like this. Imagine, I don't know if you drive or not, but
No, I don't have a It
But
did explain to me.
yeah, yeah, but I mean, every car has a maximum speed. But
Okay, yeah.
when you are increasing and approaching your maximum speed, you don't just get to the maximum speed and all of a sudden drive constantly at that speed. You kind of
Okay.
it's the curve as you're driving, right? As you're driving in your car, as you are increasing over time, increasing your speed over time. So let's say we had so let's say we had a function like this. Oh god, my lines are so bad. I must find out how to actually draw lines on here. See, the horizontal lines I'm very good at, but the coming down is where I struggle.
Yeah. It's
So
difficult.
so let's say you start at 0 kilometers per hour. So you have kilometers per hour here, and you have time on your x-axis. So over time, as you are increasing your speed, what might happen is that you might reach a, a certain speed, and then your graph will start turning around like this.
Okay.
But unlike the cubic function, it won't you won't experience a decline, or you won't reach a turning point. You will just
Okay.
keep tending towards the carrying capacity or the maximum speed. So that's what they mean by limited growth, and this is modeled by this specific function. And another example of limited growth that they give us here is the consumption of protein by households. And the reason why this function is so important is that I'm going to try and find, yeah, here it is here, right? So as the population growth, oh, okay, this is logistic growth, but it's the same kind of form as population growth. But as we get to the carrying capacity for the specific function, we have this the rate of acceleration decreases.
Yeah.
Um, and then they have an example that they've used here, and I don't know where this example is, but I have a note here on it. Where they model the consumption of protein of households, right? So what they're saying here really is that if you're trying to model the consumption of protein for households based on the amount of disposable income that they have, what you tend to find is that there isn't a direct proportionate rate of consumption across all households, right? We find that poorer households spend more of their disposable income on meat because they have less disposable income. But when you get to a point where you're making like 100 million rand a month, let's say, you're not gonna be eating 100 times more protein than a household that has only 1 million rand income. So what happens is that you start saving because you start saving your income, etc. And there might not be enough protein for everyone. So then if you did plot this example here, you'll notice that you kind of have the same kind of behavior as well, where it's tending towards the maximum carrying carrying capacity. And then they kind of use this. So I think, and then so now let's talk about logistic growth as well. Logistic growth is also similar to unlimited growth, but because we have a negative, we have this, we sort of factored in that there will be some sort of decline through this negative exponent here. So I mean, whenever I see this negative exponent, I immediately think, okay, cool. There's some sort of capacity that we are tending towards. And then they model the spreading of a virus. I mean, this reminds you of all these models that came out when the virus outbreak first happened, right?
Yeah.
So in the example here that they give, they say, a virus spreads through a chicken farm according to the following function. Obviously, this is the general function that models logistic growth. So it's 800, and it seems to me that this a that's over that's the what's it? This is the numerator, right? And this is the denominator. So this numerator, it seems like it might is it the carrying capacity? Is it?
Where are you?
On page 52.
Okay, yeah.
So is this 800 the carrying capacity? So it says here where F is the number of infected chickens and T is the number of days since the first chicken had been infected, at which stage there were 800 chickens on the farm.
Yeah.
Oh, so this 800 is the number of whatever we're measuring at the beginning.
Yeah.
Okay, so this A that's on top here is the number of things. So after 2 weeks, and then we have T over here. So after 2 weeks, if we substitute 14 into T there, and we're trying to model the spread of this virus through the chickens, we will obviously, if we substitute all these different constants, we'll know that 4 chickens were infected. And then after 100 weeks, 772 chickens were infected. And basically, the thing to remember here is that we'll never have more than 800 chickens infected.
Yeah.
Okay, cool. And then the last example, and I'm really going to end it here, is just a short discussion on uh,
Hyperbolic function.
hyperbolic growth and functions. I mean, what can you say about that? I think the important thing here is just to remember that for hyperbolic functions, which are on page 53, is that it's modeled by this specific function a over bx plus c, and if a is bigger than 0, then the function has a vertical asymptote. And if a is smaller than 0, then the function has a horizontal asymptote. Do you understand what that means, Tom McQueen?
May you please explain?
Oh, okay, cool. So if a is positive, okay, fine. So here's the general form of a hyperbolic function, right? It's given by the following: fx equals a divided by bx. I'm just going to put bx plus c. Cool. And this function kind of looks like this, right? So if we have, okay, so you have your vertical line there and you have a horizontal line here. It kind of takes this shape, right?
Yeah. Yeah.
Or this shape.
Yeah.
Cool. So what they're saying here is if a is smaller than 0, so if this a is smaller than 0, then the asymptote, an asymptote is obviously the line that the graph tends towards but never actually touches. So if a is smaller than 0, then we have a horizontal asymptote, right? So the line that the graph kind of tends towards is a horizontal asymptote,
Oh.
like that. And then they're saying here if a is bigger than 0, so if this a is bigger than 0, we have a horizontal asymptote. So it'll be, for this example that I'm using now, I'm obviously using x equals 0, but that asymptote could really be anywhere. It's just a straight line that represents, and you can obviously then reflect the hyperbolic function across the asymptotes by making, I think, now how do you do that? By making something here negative. So the inverse function. Let's see if there's any examples at the back of our book. Oh, here we go. You have the vertical asymptote and the horizontal asymptote.
Mm-hmm.
And I'll leave it to you to find out how to reflect a line across the asymptote. Can you get back to me before we start our next lesson?
Okay.
All right, cool. Otherwise, have a great evening. I'm off to have dinner now. Cool. Wait.
I actually have very much. Like, I enjoy them. So please don't be discouraged because people are not in here.
It's fine. If you and I will get 80% for the exam, it's fine. Let's see who's the last one laughing then. Okay, cool. So tomorrow, at between 7:30 and 8:30, then we're gonna do the next chapter, this killer, the differentiation. Okay, cool. Cheers. Have a good evening. Bye.
Okay, bye.
Bye.